Hello, everybody. I'm Andrei, and I work for JetBrains as a Senior Vice President of Investments, Research, and Education. Welcome to Regionals. Great things happen when great minds come together. JetBrains wants to seek out great minds all across the globe, support their initiatives, and work together to create great things that will make the world a better place. That's why JetBrains is proud to be a Global Tools sponsor of the ICPC. There are already many great minds working at JetBrains, and together we have created some amazing things, like the Kotlin programming language, for example. It keeps on growing and growing in popularity. In 2017, Google began officially supporting Kotlin as a language for writing Android applications. We have also created professional development tools like Cline for C++ programmers, IntelliJ IDEA for Java, PyCharm for Python, and also educational tools that help people learn and teach programming. The regionals are the biggest contest in the ICPC calendar. Thousands of talented people all over the world team up to solve complex real world challenges. These contests are the proving ground for future champions. But even if you don't make it through to the finals, the experience of competing in the regionals and the new friends you'll make along the way are priceless. Enjoy the ride. Best of luck to everyone.
The next problem is dice climbers, and there were no solves during the contest. Its author is Vaibhav, and he will explain the solution.
Okay, so a brief overview of the problem. So there are two players, both of whom initially are at the starting position, which is 1, 1. And the first player to reach the mth stair wins. And the game plays such that a player rolls a dice and moves ahead by the number shown on the dice. And if the player lands on a cell where the other player is present, then the other player has to go back to the starting cell. And we want to find the expected number of moves in which the game gets over. So here let's represent E of xy as the number of expected moves if the locations are x and y. And it is x's turn to play currently. Then we know that, let's say the max of x comma y is m, then the expected number of moves is 0. That is our base case. And otherwise, we have 6 other states that we can transition to, say xi, yi, where I goes from 1 to 6. So the probability of each transition is 1 by 6, and the expectation x comma y can be represented as 1 plus 1/6 of the sum of the expectations of the the parent states. And the one here counts for the move that is currently being played. Next slide, please. Okay, so in this case, we can see that there are m square possible states. Hence, we have m square linear equations where, uh, as we saw in the previous slide, if the max of x comma y is m, then the expectation is 0. Otherwise, it is 1 plus 1/6 of the sum of the parent states. Uh, we can solve this using Gaussian elimination, or in junior college also, you must have learned the row echelon form if you haven't heard of Gaussian elimination, but they are the same thing, more or less. So yeah, it is not a very difficult concept. If you have some m square linear equations here, it would take m square cube time, which would be big of m power 6, which is clearly too slow for our constraints. Next slide, please. Okay, so let's come to an important part of the problem here. So in case there were no cycles in our state transition graph, we could have just applied DP and solved for expectation. However, in our scenario, there are some cycles. An important observation here is that the max of x comma y doesn't decrease, because as soon as, let's say, a player ends up on a state on which another player is already present, the other player goes back. So yeah, in no scenario would it happen that max of x comma y decreases. Hence, what we can do is that we can fix a particular value of max of x comma y and solve for that in decreasing order. So we can start keeping the max of x comma y as m and gradually solve it for all values from m to 1. and compute the expectation for all of these values of n. Next slide, please. So in this case, we know that there would be big of m states overall that we would have to solve for. And we are solving for each value of max of x comma y. So hence that would take big of m cube per value of m. That would be big of m power 4. However, that would be too slow for our constraints as well. So here we can observe that we can only compute the expectation for x which are less than y. And so we can split it sort of into two scenarios. So let's consider the expectation as 1 plus 1/6 of summation of the parent states, which we can represent as e of xi comma yi. Then we can expand e of xi comma yi using its own equation. Let's say it depends on certain xij and yij. So we can show that we only need to expand at most one layer in order to solve this equation for xi greater than or equal to yi. And we can solve this using dp. This would still take big of m comma 4, m power 4, but it has a smaller constant factor. Next slide, please. Okay, so this is one of the crucial observations in this problem. So for the remaining states where x is less than y, where y is a fixed value of m, we can observe that the matrix is quite sparse and we don't need to do all big of m cube operations. The structure is very regular. As you can see that the 7 diagonals that are marked in yellow here and the last 6 rows, only those are the ones that would give us non-zero coefficients. So we only need to solve for those instead of the entire matrix. Next slide, please. So we can exploit this structure and basically perform Gauss elimination only on those last 6 rows. So overall, we would get a complexity of big of m into d square, but that would be per m. So overall, that would give us a complexity of big of m square into d square. And that fits into the constraints that we have provided in the problem. Next slide, please. Okay, you can further optimize this and solve it in big of m square into d by noticing that if the fixed value of the max of x comma y lies between d and m minus d, then the states are acyclic. So we can just do dp on them instead of solving the equations. So yeah, but that was not required in the current state of the problem. Next slide, please. So in general, the takeaways from this problem are that let's say you are given a Markov chain, such as in this problem. You use some way to solve a linear equation system to get some properties about it. Usually, you would find a lot of expectation problems that exploit this. And having insights such as you might have certain SCCs which you can solve for in reverse topological order can help optimize time because there might be scenarios where the graph is sparse. Hence, you need not apply, you need not solve the equation for all states in your state transition matrix. And in the extreme case, the Markov chain is acyclic and hence you can just straight away use dp to solve this.